Am I audible? Hello?
হ্যাঁ স্যার।
হ্যাঁ স্যার, শোনা যাচ্ছে।
Okay. So, key lemma. If a group H of order p to the power n, where p is a prime, acts on a finite set S and S0, those x belongs to S such that hx equals to x for all h belongs to h, then modulo p. So this lemma is very useful. The proof of this lemma is very easy, but this result is very useful. It is quite easy proof. Now you know that uh, proof S can be written as summation of distinct OX, X belongs to S distinct class. Now X belongs to S0 if and only if hx equals to x for all h belongs to h, if and only if ox hx such that h belongs to h equals to singleton x, if and only if cardinality ox equals to 1. So I can write S is summation ox, cardinality ox is 1, and summation ox, so sorry, I should write S equals to union, then I should write here union, this imply distinct class cardinality S equals to summation distinct class x belongs to S class. So I should write here cardinal number ox is greater than 1. Now what is this? Cardinal number S, that is S0 exactly, because for each x belongs to x0 cardinal number of ox is 1. So plus summation, and this is g colon gx such that g colon gx is greater than 1. as, or cardinality of orbit is equals to stabilizer index. Now, no, here is H, group is H, so I should write H colon Hx. Group is H, I should write H.
দাদা,
Yes,
রেকর্ডিং হচ্ছে দাদা?
ha.
ঠিক আছে, ঠিক আছে।
Now, index by Lagrange theorem, index is divide H e to the power n and that is greater than 1. This implies P divide greater than 1. So this implies cardinal number of S congruent to S0 modulo P. So now this result can use in to prove this theorem. Cauchy's theorem. If G is the finite group whose order is divisible by P, a prime P, then G contains an element of order P. Next day I will do a list of problem, okay, of group, list of problem from group. Proof is given by Mackay. Sigma I should write A1 to AP belongs to G to the power P such that product is identity. So A1 AP belongs to sigma if and only if AP is A1 AP minus 1 inverse. So AP is depends on AP is determined. I should write AP is determined by A1 to AP minus 1 is determined So cardinal number of sigma is cardinal number g to the power p minus 1, because last one is dependent. Okay, g to the power p minus 1. So p, since p divide g, so sigma divide cardinal p divide, since p divide g, this imply p divide cardinal number of sigma. Okay, now I act ZP on here. Okay, A1, I write K bar A1 AP goes to AK plus 1 AP A1 AK. Check that AK plus 1 AP K plus 1 AP A1 AK belongs to sigma. That means product of this element is identity, and theta is a group action. Check it. So by this theorem, by key lemma, by the key lemma, cardinal number of sigma congruent to cardinal number of sigma 0 mod p. Now what is sigma 0? Where sigma 0 is those A1 AP such that hx equals to x, right? What was s0? S0 is where is s0? X belongs to x, hx equals to x. So here I should write ak plus 1 apa1 ak, that is kx equals to x. X means our tuple for all k bar belongs to z mod pz. Therefore ak plus 1 equals to a1 for all k belongs to z mod pz. So a1 ap sigma 0 if and only if a1 equals to a2 equals to, this implies a1 equals to a2 equals to a p. AP, and product of them is I should write say, and product of a1 AP equals to identity. That means a to the power p equals to identity. So this is now identity that is identity G. I should write identity G what is the identity? I should write here identity of G. Okay, that belongs to sigma 0. You can see that. Therefore, cardinal number of sigma 0 is not equals to 0. Now, from star, what can I say? 0 mod p, as p divide cardinal number of sigma. Here I already uh, proved it that p divides sigma. So sigma 0 now sigma 0 not equals to 0. That means p divides sigma mod sigma 0. That means cardinality sigma 0 is greater than 1. So there exists as p divide. So there exists A belongs to G with A not equals to identity, such that A tuple belongs to sigma 0. This implies A to the power P equals to identity. This is proof of Cauchy's theorem. If you have any question, please ask me. This is a very important theorem. Okay. Definition: let G be a finite group G is called a P group if cardinal number of G is P to the power n for some n greater than 1, greater or equals to 1, I should write. Okay. Note that G is a P group. P, what is P? P is a prime. Note that G is a P group if and only if A belongs to G and A not equals to identity implies order of A is P to the power k for some k greater than 1. So every element has order P to the power some k. So then G is P group. Okay. Another observation: if G is a P group, then if let G be a free group. Let G be a free group. Consider the class equation since P divide CGXI as greater than 1, this index is greater than 1. This implies mod P. Now identity G ZG, this implies cardinal P ZG is not trivial. It is ZG identity, ZG identity belongs to ZG, therefore ZG greater than 1. I should write one more line, greater than equals to 1, and P divide order of ZG, this implies ZG is strictly greater than 1. This implies ZG is not trivial. So center of a P group is not trivial. Okay. And another lemma, let G be a finite group and H subgroup G and H is a P group for some prime. Then normalizer H colon H congruent to G colon H modulo P. Proof. Since here is G colon H, so I have to act H on the set of all left coset, right? Proof. And use the key lemma. Let S be the set of all left cosets of H in G. Then cardinal number of S equals to G colon H by notation. By notation, this is the notation of this cardinal cardinal number of set of all left cosets. Now act H cross S to S eta. What is this? Small h xh goes to just simply hxh. Now what is, check that this is a group action. Theta is a group action. Now what is S0? Those XH now XH is 0 if and only if X inverse HXH H. This implies X inverse H for all H belongs to H. X belongs to H, because you know that AH equals to H if and only AH equals to H if and only if A belongs to H. H belongs to H. This implies X inverse HX subset of H. Now this is conjugate subgroup and cardinality are same, therefore this implies I should write X inverse HX equals to H, as their cardinality same. And both are finite, and G is finite. Okay. So what happened? If and only if X belongs to NGH, therefore if and only X belongs to NGH, therefore cardinality of S0, what is this? NGH colon H. By the key lemma, S congruent to S0 mod P, hence NGH colon H congruent to G colon, I should write opposite direction, G colon H congruent to NGH colon H mod P. So I can conclude from here that if H is a P subgroup of a finite group, G, such that P divide G colon H, then H. Because if NGH equals to H, then NGH colon H is 1 and P divided G colon H. So uh, this contradicts the equation just G colon H congruent to NGH colon H modulo P. First Silo theorem. All of you know this. All of you know this theorem. Let G be a group of order GCD PM is 1 with n greater or equals to n. That means P divide actually. Greater equals to 1. P is a prime. Okay. Then G contain a subgroup of order P to the power I for n, and every subgroup of G of order P to the power I is less than n, is normal in subgroup in some subgroup of order P to the power I plus 1. Order proof. Very easy theorem. Now we have P divide G and by the Cauchy's theorem there exists A belongs to G such that order of A is P, i.e. There exists a subgroup generated by A of order P. So true for I equals to 1. By induction hypothesis, let there induction hypothesis there exists a subgroup of order p to the power I less than n. Induction hypothesis there is a subgroup H order p to the power I 1 less than I less than n. Okay, so I have to show that there exists a subgroup of order p to the power I plus 1 also, and it is normal. uh, H is normal in there. So G colon H, what is this? G colon H p to the power n m by p to the power I since I less than n, p divide G colon H. Therefore, by the previous result, I use the result. If H is a P subgroup of finite group, P divide G colon H, then normalizer is not equals to H. Then by the previous result, by the previous NGH not equals to H. Now normalizer of H is the largest subgroup containing H where H is normal. Okay. So and P divide colon H NGH, I using this result. Mod P. I am using just this result. Okay. So P consider the group NGH quotient H, because H is normal in NGH. Okay, so I can consider the quotient group by Cauchy's theorem. P divide this order, P divide colon. So by the Cauchy's theorem, there exists a subgroup H1 such that H and H1 quotient H is P. This implies cardinality of H1 I plus 1, and H is normal in HI. yes, H1. So by induction, we have proved a silo theorem, or silo first theorem. I should have first theorem. Definition: a subgroup P of a group is said to be silo P subgroup if order of P is P to the power n, where small p to the power n, I should write, where order of G equals to P to the power n m GCD Pm equals to 1. Maximum order of silo P. So by the first silo theorem, silo P group exists. Note that silo's first theorem, silo P subgroup exists if next we notice that if H is a P silo subgroup, then for any x belongs to G, cardinal number of x is x inverse cardinal number of H n, where cardinality G equals to P to the power n. So x H x inverse is also a silo P subgroup. So if H is a silo P subgroup, then its conjugates is also silo P subgroup. But converse, what about converse? Let P and Q be two silo subgroup. Are they conjugate? Are they conjugate? If there is only silo P subgroup P of G, then I should write H. So subgroup H of G, then X H X inverse should equals to H, because it is also a silo P subgroup for all X belongs to G. Hence H is normal in G. Now what about converse? If a silo P subgroup is normal, then what can you say? You can, normal means there is only conjugate one conjugate subgroup, all conjugate subgroup equals to H, but I am saying that if H is normal in G, a silo P subgroup is normal, then is it equal, is it unique, sorry, is it unique? That means only one silo P subgroup.
Yes, sir.
Answer. How to show? So I am showing this. Theorem. Second silo theorem. If H is a P subgroup of a finite group G, and P is any silo P subgroup of G, then there exists X belongs to G such that H is subgroup of X P X inverse. In particular, any two silo P subgroup are conjugate. Are so Silo's second theorem tells more, that if H is a silo P subgroup, not silo, H is a P subgroup and P is a silo P subgroup, then H can be embedded as a conjugate subgroup of P. H is a subgroup of X P X inverse for some X. Okay. If H is in particular a silo P subgroup, then it is equal. Proof. Proof is easy. Let S be the set of all left cosets of P. Why I am taking S be the set of left coset? You know that I am just here using this technique. this technique. See, XH inverse is subset. Same technique. Coset of P H cross S to S. What was H X H goes to same X. So by the key lemma, what S congruent to S0 mod P, where S0 is those XH such that HXH equals to XH for all H belongs to H. So XH belongs to S0 if and only if I have seen that X belongs to NGH, right? So I have seen that what X belongs to X0 if and only if it is. Okay, now what is this? S0, now cardinality S equals to G colon H, right? No, not G colon H, it is left coset of P. So I should write P. What is this? P to the power n m by P to the power n, that is m. GCD Pm equals to 1. So P does not divide S, right? Therefore P does not divide S0. This implies S0 cannot be 0, otherwise P will divide. So there exists X. Oh, I should write XP, right? S is your left coset of P, right? So I should write XP, left coset of P. So I should write here all are XP. XP belongs to H, XP is XP. Okay. Now XP belongs to S 0 because it is not 0, so there exists SP belongs to S0. This implies H XP equals to XP. So for all H belongs to H, this implies X inverse H X P equals to P for all H belongs to H. This implies X inverse HX belongs to P for all H belongs to H. This implies H inverse HX is subset of P. This implies H is, I should write subgroup because it is also a group, subgroup of P. This implies H is subgroup of X P X inverse. Done. Proof is done. So in particular, if order of H is P to the power n, then they are equal because order of X P X inverse also P to the power n. Okay. Now last one is third silo theorem. If G is a finite group and P a prime then the number of silo P subgroups of G divide order of G and is of the form Kp plus 1 for some proof. You see that what is the any two silo subgroup are conjugate, so you have to and conjugates are silo subgroup. So number of silo P subgroup means you have to find what is the number of conjugate subgroup. So you see that first class of group action this line G colon NGH denotes the number of conjugate subgroup of H. So if P is a silo P subgroup, you have to find the number G colon NGP, because we have seen that conjugates are if P is a silo subgroup, then all conjugates are silo P subgroup, and conversely if Q is a silo P subgroup, then Q is conjugate to P. So you have to find what is the number of conjugate subgroup of P. That means this G colon NGP, sorry, you have to find. Okay. So we need to find G colon NGP as Q is a silo P subgroup if and only if Q is conjugate to P. Okay, you have to find the number G colon P. Now G colon NGP divide order of G. So number of silo P subgroup divide of G divide order of G. Now next, first part has proved. Now we have to show that it is of the form Kp plus 1. Okay, Kp plus 1. let S be the set of all silo P subgroup of G. P cross S to S theta. I write here some X. No, I write okay X and Q goes to X Q X inverse conjugation action. Check that it is. So what is S0? That Q belongs to S such that X Q X inverse is Q for all X belongs to P. X Q X inverse is equals to Q. Now X, that means what? For Q belongs to S, if and S0, if and only if X Q X inverse equals to Q for all X belongs to P, if and only if P is a subgroup of NGQ, because X belongs to NGQ, right? NGQ definition is that those X belongs to G such that X Q X inverse equals to Q. So P is now NGQ is subgroup of G and P is a silo P subgroup of G. That means maximum prime occurred in order of P. Okay, maximum prime P occurred in order of P. This implies P is also a silo subgroup of NGQ, but Q subgroup of NGQ are silo subgroup. And Q is normal. This implies P equals to Q. You know that if silo P subgroup is normal, then they are equal, right? Therefore, what happened is cardinality S0 is singleton P. So by the key lemma, cardinality S congruent to cardinality S0 modulo P. This implies cardinality S congruent to 1 mod A, and we have the proof. So I finish the Silo's third theorem. Next day I will do some problem of proof theory, or some classification problems, some standard problems, SN from. Okay, if you have any question, please ask me. All are the main tool is group action here. Okay, you have to understand the technique, which group action you have to take in particular problem. Okay, there are 3-4 group actions which mainly occurs here. 3-4 types group action. Okay. Have you any question? Okay.